official start. So thank you all for joining. So it's a pleasure to present the live demonstration of of SMARTEX, our developed solution funded by the open call of EU Robin. Let me enlarge the slide. Okay, so before going into the meeting points, but this is a quick overview of the agenda. So in the beginning, we will introduce EU Robin. Rebecca will do this. And then I will go into details of SMARTEX and the architecture that we've developed. And finally, with the live demonstration from our laboratory of the sorting system. So I'll leave the word to you, Rebecca. I will stop sharing and leave the word to you. Thank you.
Yes, thank you for your invitation. And okay, I will start the presentation very soon. See how it works here. Here it is. Okay. Can you see the screen?
Yes.
Perfect. So, yeah, thank you. I'm Rebecca Schedel-Warburg from DLR, and I'm the project manager of the European funded network of excellence on AI-powered robotics. The coordinator is my boss, Professor Dr. Aline Albuschäfer. And yeah, our project is in the last year, and we started in 2022 with 31 partners from 26 European cities, 7 industrial partners, and 26 academic partners. Here's the map with all the points and all our partners. We have in our project 3 application areas. One in robotic and manufacturing for the circular economy. The second is personal robots for enhanced quality of life and well-being. And the third one is outdoor robotics for sustainability communities. Then we have the scientific work packages, and they are interact, know, learn, and human-centered robotics. And you can see a circle. The gray ones are our application work packages. The blue one are the scientific, and in the center is our Eurocore. I will talk about that in a moment. It is a network, of course. We have several possibilities to join in and what we are doing, science-industry dialogue, dissemination, exploration, and communication, of course, cascade funding, scientific workshops, cooperative competitions and hackathons, and also some other programs. And in the middle, you can see here, it's Eurocore. What is Eurocore? Eurocore is a repository. We have a website, and it's linked to AI on demand. It looks like this here. And we have some records at the moment, more than 48 records. We have a digital twin. It's really very good revenue from our partner, University of Bremen. You can choose, for example, a robot and use a new software path planning or something like that. And we have a marketplace. That means we have hackathons and cooperative competitions, and the teams are in. They say, yeah, we have our strength in this and that area, and we will or we provide here some modules like maps, codes, etc. Then, yeah, we have cooperative competitions. That yeah, for that we created a new name. It's a competition, and the first time, or to be honest, it is worldwide. The first one took place last 1.5 years ago in North Sea. There we had a lot of teams there, and it is like this. You can provide your modules data in our repository for transfer, and it could be used within these 3 application areas: industrial, service, and outdoor robotics. And you get points when people or other teams use your modules and data, and that is the reason you could win a lot better. Or the people use it, or you use other things. It worked quite very well, and we had 23 teams there, 150 participants. It was really a great experience. We had 14 robots there, and yeah, up to 90 modules in Eurocore. Then we have another thing in our network activities, the cascade funding. Yeah, we could expand our project from 7 countries to 14 countries. We have 38 beneficiaries. Yeah. And now we have over 29 participants all over activities, our activities. And yeah, we had several calls. First call for support program with 8 beneficiaries, second call with 9, third call was with also 9 beneficiaries, and first call for collaborative projects. And there is SMARTEX, one of our beneficiaries, and we are very happy that you are one of the 12. And yeah, our partner, Danish Technological Institute, was your host. And yes, that was my presentation.
Thank you very much for this introduction and for giving the context. I'll share my screen, my slides again. Okay. So let's dive into SMARTEX, our solution that is an acronym for Scalable Machine Learning and Hyperspectral Recognition for Textile Sorting. So before going into details, let me introduce quickly the team behind SMARTEX, which is Stam, the particular team that helped develop this project. 2 of them, of course, are present here today, me and Francesca, my colleague. But overall, Stam is an engineering consultancy company operating for over 25 years and actively operating in the research and development area in several European projects and Cascade funds. Our business unit is specialized in robotics and automation and mechatronics, and has a long experience in developing similar solutions based on machine learning algorithm and different perception systems. What is the main motivation for SMARTEX is to move from, of course, from standard sorting, so sorting of textile materials which have reached the end of let's say the first life probably, and needs to be processed. Standard sorting is the manual, of course, the basic process, and then there is already, of course, existing automatic sorting solutions which help in reducing the human effort and increase efficiency, but are mostly limited to in terms of garment types and generalizability. So our aim with SMARTEX is to bridge this gap and try to augment the set of materials and compositions to work on compared to existing algorithm. So to try to push this state-of-the-art forward, and of course boosting efficiency. So we tried also to reason not on a model level, but also on a system, on a whole system architecture level. So the objectives of this project were detailed according also to the challenge raised by Robin, and these are the three main objectives. So the first one is to acquire a new dataset, textile dataset, of course using a hyperspectral camera, which tries to push forward the variability and the coverage of different materials, material compositions, so also blended materials, trying to vary colors, sizes, and origin. This is the first objective. The second one is, of course, to develop the machine learning model to work on this data, to address the classification or separation of textiles or garments based on their chemical composition. And this works, as we will see, on different levels of granularity. And finally, to demonstrate the solution, so to develop a system, a proof of concept system, to perform this end-to-end perception. So starting from the garment and the acquisition sensor to a decision. We started from our setup, which includes the following components. We have the main sensor, which is a hyperspectral camera operating in the NIR, so near infrared and shortwave infrared 1 ranges, so from 950 to 1750 nanometers. We have also a supporting camera, which is an RGB camera, which we don't use actually for sorting, but we used for dataset acquisition purposes. So as you will see later in the slides, having so the hyperspectral camera does not carry color information since it operates in the non-visual range. But then we have the RGB camera to provide this augmented view of the garments, which will be beneficial for annotation, as you will see. We also have a conveyor belt, so in order to facilitate the acquisition with this camera, which is line scanning camera, meaning that it acquires one line at a time. So we will need mechanical movement of the object in order to acquire the full object. This is a typical setup in the sorting infrastructure. Of course, we also have the supporting lamps, so the lights the calibration unit, and the PC, which is dedicated for this station, powered by Ubuntu and ROS. So as you will see, the system is developed using ROS to also support the scalability and the integration with other actuation systems. So the first objective, so the first set of activities which were focused on the dataset acquisition. In this phase, we have collected a large number of textile units or garments. These were both used garments with known composition, and also samples obtained specifically with certain compositions in mind in order to augment the size of this data set, and with very focused compositions in order to guarantee the coverage of the distribution of the garment distribution. And these were obtained from various providers of textile materials. And we've covered in the data set around 7 overall materials, of course, in addition to blends between them. So starting from garments, we move to data acquisition, which is the actual acquisition of the data set. So we've also developed a system based on on ROS and interfacing with the hyperspectral camera to acquire data from both the hyperspectral camera and the RGB. As you can see in this in the acquisition phase, we have both streams of the two sensors, and then we save these data. They are not meant to be synchronized, so we don't have pixel synchronization, but they are, so the RGB image is used as a reference. And then the user can, of course, this system is also open source, and will be embedded in Eurocore at some point. The user then assigns the composition, so it's the ground truth of the actual composition of this material, and this is obtained from the label or from any or from analysis or from some source. And then from there we have this stacked view of both the hyperspectral and the RGB input. From there we can easily separate background and foreground classes, and then we perform a final step of annotation, which is manual, in order to select the non-textile pixels. This cannot be done automatically, so we initialize the two classes, background and textile, and then the user using CBAT, which is a system used typically for segmentation and then the labeling or annotation in general. Overall, the data set contains around 100 garments. So these are the distributions of the garments, both pure and blended. We also have covered the non-textile pixels or areas, which can be zip lockers or buttons, plastic or metallic buttons, so on. Of course, this data set was also contributed to the community on Zenodo, and it was also integrated as part of Eurocore community on Zenodo, so it's also listed in Eurocore community. So the next phase is the model development. Of course, this is the main set of activities that followed the dataset acquisition, and here we focused on formalizing the task that we were interested to solve. So the task that we were interested to solve is classifying on pixel-wise, so on pixel level. So we start from pixels, and of course, pixels are inherit the composition of the garment overall. And we want to learn a classifier, a classifier which assigns a label or assigns a prediction to each pixel. Sorry. Okay. So the way to proceed is to so in order to both be able to solve pure materials and blended materials, we opted for a general settings of this problem, which is multi-label, multi-class classification. What this means is instead of each pixel having one class, so either, for example, think of other kind of classification problems where, for example, you want to know if the object is a dog or a cat. So it's a multi-class classification because we have several classes, but then each prediction is assigned one class. So it's either a dog or a cat. In this case, the setting is more general because we have multi-label. So an object can be cotton and polyester, essentially. So if it is a blend. So this setting allowed us to design one model for both pure material and blended material classification. And so in order to pre-process this high dimensional data, because the hyperspectral camera produces 255 channels, in order to compress and pre-process this high dimensional data, we rely on an autoencoder, which is a neural network used to compress basically data into few dimensions, using this end-to-end training for reconstruction. So the network learns to compress and then decompress the data, basically. And the way this works is that we enforce that the reconstruction, so at the end of the compression and decompression, the data remains as close as possible, the input and the output. And so this compressed version is what we use for, so in the middle, if you can see it here, the latent representation is what we use for the subsequent tasks. Of course, the main task is the classification. So this is for the classification. So for predicting what materials compose the garment. Then from there, we moved one step forward, which is estimating which material is more present in this garment. So on the latent space, we formalize the task of dominance estimation, which is sort of a discretization of the actual composition that we see on labels, which is, for example, the percentages of each material within the garment. In order to make this simplified for a neural network to predict, given this limited amount of data, of course, because at the end there are 100 data elements, which is still a large number of garments, but in order to simplify the composition prediction, instead of predicting the actual percentage, we predict which material is more present. So in case of two material blend, we basically predict if one of them is greater or if they are roughly equal. So this is modeled as a SVM, as we've said, as a classifier. So it's a simple classification problem and solved on top of the latent space. Of course, this makes the system more efficient since we share the representation phase between both the classification and the dominance estimation. And of course, for pure materials, we don't predict dominance since they are predicted to be of single material. So this is the flow of the pipeline of the machine learning model, basically. So starting from input data, and then what operations what modules we use in order to arrive at the final prediction that we will see them in the demonstration. So this is the benchmark that we have obtained during the development phase and during the validation phase. Of course, in order to preserve generalization and to make sure that our model can be introduced to real life scenarios with less degradation as possible, we have to make splits based on garments. So during the training, during the cross-validation phase, the splitting between training and testing was not performed randomly, but was performed using based on garments. So a garment can only appear either in the training set or in the validation set. And based on this, we've obtained these results, which are quite promising. We report here the pure materials benchmarking, and of course the blended materials, which is more challenging. So the accuracy, the F1 score is slightly lower. And of course, this is the pixel-wise benchmarking. We then move to garment-wise benchmarking. So the way we move from pixel-based predictions to garment-based predictions is using simple voting. So in this case, of course, voting of pixels of a single garment will lead higher accuracy, since we don't need that all pixels agree on the correct prediction. So this is the overall architecture of the system as a whole. So we have a ROS-based system, which is composed of 3 main nodes. So the first node is the camera node, which is responsible for interfacing with the hyperspectral camera. It's in C++. It's basically a driver for the camera, and it publishes 2 topics, which are the HSI Viz, which is a visualization of the footage of the hyperspectral camera, which is of course a reduced version of the full data, since it only publishes 1 channel of this data for visualization purposes. And then it publishes also the full cube, so the hyperspectral cube, to the line processing node, which is the main processing node, which receives this data and performs the following tasks. So first, it detects garments on the conveyor belt. So it detects the start of the garment and the end. It performs classification and aggregation of results from each line, from the classification of each line. Then it produces the summary report, which is the result, basically, which is communicated also via another topic, ROS topic. And finally, it does some logging in order to have some logs to inspect afterwards. The garment summary is the result, which is communicated, as I've said, using a ROS topic, which is we believe it's a way to make the system extensible to other modules, for example, actuation modules, a robotic arm, or or another subsystem which will make decisions or take actions based on the class or on the garment type. And this is, of course, in our case, used only for visualization, since we focus on the perception part and the visualization. So as we have said before, this is the essentially the output of the system. We have a detection. So we have the starting line and end line of each garment with timestamps. This could be this may be very useful for another subsystem which might need to actuate. We have a mask, which is indicating which pixels belong to the garment and which pixels belong to the background. We have the classification, which includes the number, so it includes which materials are present in this garment, so 1 or 2 in this case. We have the dominance prediction. So dominance, as we have said before, is a rough estimation of which material is more present than the other, which is a discretization of the percentages. We have segmentation, which is basically the raw prediction of the system, which is pixel-wise. So we also provide a few of the pixel-wise predictions. And finally, we have also the non-textile pixels, which are shown so in the mask. So this is the user interface that we will soon see in action. It's composed of the following elements. So this is the live view. This is the footage that we've mentioned before, the visualization footage from the hyperspectral camera. Below we have commands to control the cameras, to start acquisition and to stop acquisition. On the right we have the output. So we have on top a list of all garments that have been detected in this session, which is, of course, can be cleared. Then we have preview, which displays the mask, the segmentation mask. And this is the legend of the mask. So pixels are colored, and each color would correspond to a material or a blend. Okay, so this is the live demonstration time. I will jump to the demonstration place, and I'll be right back with you. So as you can see, this is the webcam. So this is the PC, which displays the conveyor belt on which I will put the garments next, and I will also share with you the screens, which is the user interface of the application. Okay, so I suppose you can see my screen. Yes. So this is a slight modification of the screen that I've shared. So I can control the camera from the application to start acquisition and stop the acquisition, but I need to actuate the conveyor belt manually. Also the light, which is reasonable. So I'll start putting the one garment, and this starts the lights. Okay, as you see, the acquisition, the live view, and you see it's pretty responsive. So although the garment was not finished yet, we have let's say an initial prediction of the class. This is useful because this is a long garment, for example, and by the time it ends, it will be quite distant from the camera. So having an initial guess of the prediction would be useful. So we can start off with some pure materials, and then move to some blends. This is a nylon material. So of course we can also see the masks. This is the mask so far. When it ends, it will be the whole object. We have some non-textile pixels like the buttons. This is acrylic. This is the polyester. And okay, let's put some blends. This is a cotton polyester blend. So this is the way that we chose to visualize this as cotton equal polyester, polyester equal cotton. So it's an indication of the fact that this blend is roughly equal. This is another example. Cotton polyester. In this case, we have more polyester predicted than cotton. This is a jumper, some wool with some acrylic, typical for jumpers. This is cotton polyester, the t-shirt. Okay, and yeah, so as you can see, it's quite responsive. It tries to give a prediction early on, and this is the view. Of course, you can stop acquisition, and of course inspect the objects that have been acquired. They are segmented with color, which corresponds to the material that they are made of. Yeah. So let me get back to the desk. Stop sharing. So yeah, just final remarks on the challenges and limitations that we think could be interesting for future development efforts. So that the small percentage blends, such as these blends where elastan plays a role, typically with under 5% of presence in the material in the blend, are quite challenging for hyperspectral sensing in this range, in our range, the SWIR1 range. So it requires some longer wavelength coverage. We also have seen the challenges of predicting the compositions since they so imagine that we have a blend of two materials, in the simplest case, cotton and polyester. In order to robustly and reliably predict the composition, even if discretized, would require a coverage of different cases. So in cases where we have 90-10, 80-20, or 20-80, for example, so the other way around. And this could be difficult in practice because some of these compositions are less used, so are less less common, and so having of course this robustness require investments on the data set richness. And of course, as usual, the response, so the hyperspectral signal is depends on the chemical composition, but is also affected by other parameters like the texture, the finishing of the garments, and these all need to be taken account into data set acquisition and collection, and this is quite challenging, and then could be a source of future development. And that's it. Happy to take your questions. Thank you for listening.
Yeah, I have a question. How many different clothes types do you had in your test?
So you mean number of elements or types?
Number.
Yeah, there are 100.
Okay.
So between 100 between normal clothes, so clothing items or samples, which we obtained for the purpose of covering difficult to find garments, because in order to be sure that we are obtaining the right material, so the material with the right composition, it has been either search, so look into labels and then see what this material is made of. Do we need it? Do we not need it? And we perform this, and also in parallel acquiring materials with this specific, so searching on the catalogs of these websites which sell the samples, and searching with the right combination composition, and then buying these samples. So 100 between both of these, roughly half.
Okay. And what are your plans with these results?
Yeah. So it would be interesting to push this development even further. So maybe trying to incorporate blends of more than two materials. Of course, this would require even richer data set, which covers even more combinations. And yeah, maybe looking into augmenting our sensing capabilities with the richer hyperspectral sensing. So going also to the range of SWIR2 to obtain better differentiation power between also the small occurring material, small percentage materials.
Mm-hmm. And do you have also contact with companies who are dealing with old clothes?
Not at the moment, but it would be interesting to see how this could be used in practice for for the reuse or yeah.
Mm-hmm. Yeah, and I know it's a big problem in Europe. I think over the world that we have too much clothes, and I know that a lot of people are on the on the lines and sort the clothes, and it would be great to have your system with some robot arms to select things. Only an idea.
Yeah. That's of course could be a great use of this this development. Of course, we will. So we will make sure to make good use of this development opportunity and try to look how to move it closer to applicability and also maybe get some feedback on how to improve it.
Thank you. Very great. Congratulations.
Thank you. Thank you. I don't know, Francois, if you want to add something or if you have any doubts that we can.
No, I think it was definitely perfect. Thank you very much for the presentation. The hard work as well. I followed the work from the start, so it was very, very nice to follow. So thank you for especially thank you for this work.
Thank you. I appreciate it.
I hope you're going to be able to work further on the system and exploit it one way or another in the future.
Yeah. We will have to make sure to do this. Okay, so thank you for joining, for listening, and for the feedback. I think if you have no further comments, we can close here. Of course, I will share this. We will share this on YouTube, and we will share the link with you. It would be great if you, Robin, could share it or maybe on some channel.
Will do.
Thank you.
Yes.
Thank you very much.
Okay.
Have a nice day.
Thank you very much.
You too. Bye-bye.
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 Bye.